speak here. I'm probably going to become terribly confused with all of this equipment. I think I'll use this screen, and when I remember, this screen also, for most of the talk. And then at the end of the talk, I may, if there's time, access a couple of slides on the computer here. So that's the reason that there's nothing here in the middle. So I hope that's not too inconvenient for you. So the idea is to give a survey here on a very new subject called discrete tomography. And in fact, it's a subject that I spent a little bit of time working on, but that's some years ago. So I already feel out of date, and you know how it goes. You very easily lose track of a subject. But anyway, my intention is that this survey will be reasonably up to date, hopefully maybe even completely up to date. So what is discrete tomography? Let me try and give you the idea on this picture here, and then I'll come back and talk about all kinds of related issues. First of all, we should give credit to the inventor of the term, Larry Shep. And now, this is my first problem with the technology. The laser isn't working. No, it says laser, but it's not working anymore. Okay, so the old-fashioned way. So Larry Shep at that time was working for AT&T Bell Labs, and he coined this term discrete tomography. So that the subject dates from 1994, when there was a mini symposium, one-day symposium at AT&T. Now, rather unusually, I don't know how unusually, the subject actually comes from a more or less real-life application to physics, and it arose from a question that a physicist called Peter Schwander, who was at that time at AT&T, asked to Larry Shep. He had a problem that he wanted to solve, and it was from crystallography or electron microscopy, and in particular HRTEM. And here's the idea. You have a crystal of some kind, and you want to know the structure of the crystal. Ideally, you would like to know the position of every atom in the crystal. And maybe there are even several kinds of atoms. And so you model this in the obvious way by discretizing. You could, for example, take the positions of the atoms to be points in the integer lattice. And then the technology allows you to make certain measurements of the crystal, and you want to reconstruct the positions of the atoms from these measurements. So what are the measurements? The measurements are what I call X-rays, discrete X-rays. I'll just use the word X-ray here. Sometimes they use the term projection is used, but that's a little misleading. So what you do is you take a direction. Let's say this direction here specified by this integer vector -2, 1. And you simply count the number of the points in your crystal, which is indicated by the red dots here, on every line parallel to that direction. Now, because your points only lie in the lattice, of course, you're only interested in what I call lattice lines. Those are lines passing through at least 2 points of the lattice. And you can also think of the direction of the X-ray as being specified by the corresponding line through the origin. So you're looking at all lattice lines parallel to that given lattice line and simply counting the number of points. So, for example, if you take this line here, you see we have 2 red points, and so the X-ray records the number 2 at this position. So you can think of the X-ray as a function then. It'll be an integer-valued function, non-negative integer-valued function, defined on some orthogonal space plane to the line that you're considering. So one thing I'd like you to be clear about right from the outset is that one X-ray gives you actually quite a lot of information. If I want to talk about a single line, I'll use the term X-ray beam, or one beam of an X-ray. But this particular X-ray gives you not just this number 2, but it gives you all of these numbers So all of the line counts on lines parallel to that particular direction. So it turns out then that there are machines which actually can effectively make these measurements. During the one-day symposium back in 1994, which was actually held at Rutgers, there was a side trip to AT&T, and we found ourselves in a small room, and most of this small room was filled by a machine which makes these measurements, and I'll talk a little bit about that later on. So what Peter Schwander wanted to do then was he wanted some mathematics which would allow him to reconstruct the position of, for example, those red points there, given several measurements of this type. It should be clear to everybody here that one measurement is not going to get you very far, right? Because these numbers here would be just the same if I shifted all the red dots by one lattice position up or down. So you're going to need at least two measurements and perhaps more. So this is what we're going to talk about. Yes?
Everything F is finite?
Yes. Yeah, the sets we're going to consider are finite because we're thinking about crystals which have, of course, very many, but a finite number of atoms. Yeah. Yes, please feel free to interrupt me with any questions. So that's the idea, and perhaps a little explanation of the word tomography. Most people, I think, are familiar with the word nowadays from computer tomography, which is the mathematics and engineering behind the CAT scanner in medicine. And you can think of this as a kind of a continuous version of the whole business. Think of an X-ray. You go to a doctor, you get an X-ray. What does it do? It measures how much stuff is in you on every line parallel to the direction of the X-ray. So this is a continuous version of this problem. Now, your first objection, among many during my talk here, might be, well, you know, crystals are three-dimensional, so why are you showing me two-dimensional pictures? Well, it really is essentially a two-dimensional problem, and I'm trying to just show you that by this slide here. So this is supposed to be a three-dimensional crystal of some kind. We want to determine the structure with the analogous measurements now, which again are going to give you line counts along every line parallel to a given direction, say the vertical one. So, for example, at this position here, we see that the function has value 2 because there are two red dots on that line. Well, if you have measurements of that type, and you can solve the two-dimensional problem, then you can simply restrict to any lattice plane, solve the problem in that two-dimensional plane. Are you all with me here? Because if you just restrict the function to the two-dimensional plane, it will be one of those functions. And then you can build up the two-dimensional slices, assuming you can solve the two-dimensional problem, and that will solve the three-dimensional problem. Now, all of this is assuming, of course, you have exact measurements, which is never the case in real life. But for virtually all of my talk, I'm going to assume that the measurements are exact. I'll touch on the stability problem right at the end.
Isn't it possible that in some way the three-dimensional problem will be easier? So you can get advantage by having another dimension?
Well, it's true that the story doesn't end with two-dimensional problems, but all I wanted to convince you of at this stage is that if you can solve that one, then at least in principle you can solve that one. But yes, there are essentially three-dimensional problems which actually are still remaining to be answered. In any case, the whole problem is remaining to be answered. This is very much a field with loose ends and unsolved problems. I won't be talking about the physics, principally because I don't understand it. By the way, you shouldn't get too emotionally attached to any numbers you might see on the transparencies, like the 5 there, because they come from different talks I've given in the past. And this one is just copied from one of the papers by Peter Schwander's group, and it's just supposed to give you some idea that there might actually be some real physics behind it. These are pictures resulting from a particular technique called quantitem, one of these high-resolution transmission electron microscopy techniques.
Do the continuous methods not work?
Yes, I'm going to come to this in a minute. The answer is that they don't work, and this is really why Peter Schwander went to Larry Shepp in the first place. I should mention, for those few of you that don't know the name Larry Shepp, that he's a leader in the field of tomography, an expert, and so he would be just the sort of person to ask. But I think even he was surprised that nothing essentially that was known could be brought to bear on these problems, because of some restrictions which I still have to mention here. So I'm going to begin to describe what's known about this problem. And first of all, I won't bore you with notation very much, but just in case you see it from time to time. In any case, it might be inconsistent throughout the transparencies here. What we're agreeing to work with here then is a class of sets, finite subsets of the integer lattice, usually in the plane, but let's just allow ourselves to talk in higher dimensions if we wish. And we're talking about taking these measurements called X-rays, which are taken parallel then to vectors with integer coordinates or parallel to lattice lines. And we might want to restrict the class of sets. For example, just consider sets of no more than 100 points or sets with particular properties. So we need to allow ourselves to do that. And we want to then understand when we're going to be able to make this reconstruction. Now, there are many related problems, several related problems to the basic one of reconstructing the position. One is uniqueness. That's a very basic one in all inverse problems. Do you have one solution or do you have many? You hope you have one because that makes it simpler. So we would say that a class of sets or a particular set is determined by X-rays parallel to a particular finite family of directions. Well, if it's uniquely determined by those measurements. If any other set with the same measurements, this is my notation then for X-ray of a set. If they're always the same, then the two sets must be the same. So that's natural. And that leads to a problem which you can call uniqueness, depending on the class of sets and the finite set of directions concerned, which you can set up formally if you're interested in computational geometry, which I suspect that some of you might be. But, you know, it takes a little bit of time to do that. So I'm not going to bother to be formal in this talk. So you would call that problem, then, uniqueness. And it would depend on the class of sets and the directions. The related reconstruction problem, and also, along with it, you have a fundamental problem of consistency. Now, rather than wade through the technical details of all those things, let me just give you some simple examples, because this should pretty much tell you what's going on right here. Look at these three simple examples. In the first picture here, I've taken some measurements. My measurements have come back as follows. I've taken two X-rays, one in the vertical direction and one in the horizontal direction. Now, the vertical direction X-ray has told me that there's one atom on this line, that's indicated by this one here, and there's one atom on this line, and zero everywhere else. And the horizontal ones, again, are one here and a one here and zero everywhere else. So what could the solution possibly be? Well, the solution could be a crystal consisting of just these two red points. That would satisfy the measurements exactly. On the other hand, it could be this blue crystal of those 2 points. So there's an example, the most basic example of non-uniqueness. So that shows you that two X-rays in general won't be enough. This one here, if the measurements turn out to be 2 and 2 and 2 and 2 and 0 everywhere else, then obviously you've only got one solution, which is indicated there. So there you do have a unique solution. And here is an example where you don't have a consistent set of measurements. If you have a 1, 1 and a 2, 1, well, you don't have a crystal which satisfies that data, because the 2 means that you would have to have 1 here and 1 here, but then these ones are already used up, and there's no place here for your atom, which should be apparently there according to that horizontal measurement. So uniqueness and consistency as indicated then by these examples. In real life, what's going to happen? You've got a crystal, you take some measurements. So those should be consistent, right? Well, the trouble comes, of course, with errors in measurement. If there are errors, then even though the measurements have come from a real crystal, the measurements may no longer be consistent. So one has to consider this problem. Now, if you look at these pictures, it doesn't take long to realize that there's a very obvious model for all of this that you see here, which is just 0, 1 matrices. If I take a 2 by 2 matrix and just think of putting a 1 where you have an atom and a 0 where you don't have an atom, you've got yourself a binary matrix, and the measurements, the X-rays, these ones that I'm talking about, horizontal and vertical, would just correspond to column sums and row sums. So this problem, where you have two X-rays in the two coordinate directions, is exactly the problem of trying to reconstruct a 0, 1 matrix from its row and column sums, and that actually predates the whole subject of discrete tomography by quite a long way. And a lot of work was done by Reiser and other people back in the 1950s. Those results tell us already something, which is that all of these problems can be solved in polynomial time in this situation. So if you just take two measurements in the vertical and horizontal directions, all the problems have a polynomial time solution. Now the problem is that, as you can see by the simple example here, you'll almost never have uniqueness if you just take the two measurements. So if you take a real-life crystal, you just take two X-rays, there'll be many, many solutions, so that's not very good. So you'll want to take more measurements than just the two, and then you can't use these polynomial time results. So what happens if you take more than two measurements? Well, I think this is what Ron Graham, who was present at that one-day symposium back in 1994, called the dark side of the force. You've got a very unpleasant non-uniqueness. It doesn't matter how many measurements you take. You've got, unless you make some kind of restriction, you'll have non-uniqueness. And I just want to indicate the very simple idea that's been independently hit upon by several people, an inductive procedure to show you this non-uniqueness. I'm trying to position these transparencies so that it doesn't get lost in the darkness up there. So what I've got here is 4 directions. Okay, these are 4 lattice directions here, and I want to construct an example of 2 different crystals which have the same X-rays in those 4 directions. So the idea is, it's very simple. Just do it inductively. Order these directions. Take the first one to be horizontal, and then the crystal with the right at the top left here, with a single atom, blue atom, and a single red atom. Obviously, the red and the blue have the same measurement in that one horizontal direction. You just record a 1 on that line and 0 everywhere else. Now, to take the second direction, say to be the main diagonal one here, to get an example which copes with the first 2 directions, the horizontal and the diagonal, you take the example that you had before, you just shift it away, doesn't matter, far enough to be disjoint, say, and then switch the red with the blue and the blue with the red. So you end up with these 4 colored dots here, and if you look at the 2 reds and the 2 blues, you'll see that you have the same X-rays in those 2 directions. That's just an affine copy of the example you've just seen. Now take a third direction, which is this one here on my example. Take the example you have for the first 2, shift it, change the reds and the blues around, and now if you look at this picture here, think of the 4 red dots as one crystal and the 4 blue dots as another crystal. I want to check at this point that everybody understands, because I know how it goes with talks. You know, we need to make sure of the basics here. So what do I mean when I say the red dots and the blue dots have the same X-rays in those 3 directions? I mean, take a line parallel to this direction. Right? Take, for example, this line. Well, that hits one red dot and one blue dot. So the measurements are the same. Right? The count is the same. Whatever line you take parallel to this direction, you'll count the same number of reds as blues. That's what I mean by the same measurements. And then finally, you just do the same thing again, and you get an example for these 4 directions. And clearly, you can do this for any finite set of directions. And here again is another picture, labeled number 4. Where mysteriously now blue has become green. But again, it's supposed to be the same thing. With these 4 directions, the green and the reds have the same line counts. It's obvious, though, now, isn't it, to a geometer what that is? That's just a projection of a 4-dimensional cube with the vertices labeled alternately red and green. So really, that's all you're doing. You're just embedding that projection in the integer lattice to make sure that everything has integer coordinates. Why? Because we like integer coordinates in discrete tomography. Okay? And I need to say more about that in just a second. Let's go back to the practicality of it, or the practical issues. Is this any kind of a model for a crystal? It's not a very good model. There are not many crystals that look like the set of red points. They tend to have lots of atoms close together. But it might not be such a bad example if we take the photographic negative of what you see on the screen. So imagine a crystal that has all of the points in this big array containing atoms on those points, except for the green positions. And then another one that has, again, all of the atoms in the whole array, except for the red points. Well, those, again, will have the same the same X-rays in those 4 directions. So now you get a more realistic model of this unpleasant non-uniqueness phenomenon. So at this point, I want to back up a little bit and tell you why we're looking at lattice directions, and maybe even why we're looking at lattice directions of this particular sort. It would be very nice if we had a machine that could take an X-ray in a direction with irrational slope, because then we would just need one. Can you see that? If I take one X-ray in a direction with an irrational slope, you're going to determine the position of every atom just with that one X-ray. Unfortunately, the physics prevents us from doing that, because you just need enough energy to make the measurements. So you have to make measurements along lines where you've got many atoms lining up. So that's why you're restricted to lattice directions. It would also be nice if we were able to take arbitrary lattice directions. So, for example, not just 2, 5, but maybe 22, 53. But that's, again, not allowed from the physics. And the reason from that is it's a resolution issue. To resolve the picture in this method quantitem, you have to have sort of a reasonably wide spacing between the lines. So in practice, then, what happens is that you're restricted to integer directions and with small integer values, maybe no more than 5. Moreover, you can't take that many of them, because every X-ray you take stands a chance of damaging the crystal. So in practice, maybe 3 or maybe 4, and then you begin to make too much, change the crystal too much. So all of these issues, which I finally got around to here, were ones which make the conventional techniques of computerized tomography absolutely useless. But it also makes the mathematics more interesting, more challenging. Let me leave that there. So now I'm going to go on and describe a little bit what's known. And this is just in survey style with no details, essentially. Just an outline. There are many ways that you can go. Once you realize that it's hopeless, your uniqueness has evaporated, there are many ways you can go. Just settle for less somehow. You can, for example, I don't want to talk about all of these, but you could try to determine among many solutions a typical solution. perhaps, somehow. Or perhaps there might be a number of points which are common to all possible solutions. You could call that a core, and you could try to determine that. You might restrict the number of points, or you might restrict the type of lattice, finite subset of the lattice you're considering in other ways, and I'll touch on that later. But first of all, let me give you the basic results from the algorithmic point of view. So as I said earlier, you can set this thing up formally. For example, the consistency problem that I mentioned earlier, you can take, again, there's been a little change in notation here. The class E of finite sets has now become a G. I'm considering a finite set of directions. Actually, you can put all of this in higher dimensions, but let's not worry about that. And an instance of the problem then, set up algorithmically as a decision problem, would be a finite set of, well, we can't really call them X-rays. They might not be. They'll just be potential X-rays. So non-negative integer-valued functions defined appropriately. And then the question is there actually a crystal, a finite set of points, whose X-rays are equal to those measurements? So that's the consistency problem. And then you can set up the same, the uniqueness and reconstruction with the same kind of language. So with that little background there, here are the results in a nutshell. The first ones I've mentioned already, which are these polynomial time results when you have just two directions, two measurements, which go back to that work on binary matrices. And for three or more, the sad story is that everything is NP complete. So whenever you take three or more X-rays, all of the problems, consistency and uniqueness and reconstruction too, become NP complete. This is work I did with one of the principal contributors to the field is Peter Gritzmann at the Technical University in Munich. And he and a PhD student of his and I got these results some time ago. Now, yes?
So what problem did you relate it to?
Yes, I'll just touch on that on the next transparency.
Oh.
Thanks for asking the question, though. I wasn't sure when I prepared this talk how much I should say about NP completeness. I'm sort of assuming that most people are familiar with polynomial time and NP. Would anybody like me to say just a few words about that, or shall I just leave it? Everybody's okay with that? It's a little Easter egg picture of the whole business here. Okay. All right, so what problem do we relate it to? Well, let me just outline on this one transparency the general plan. I've been unfair to people over here now, haven't I? But okay. So you make a reduction. We're talking about three or more measurements. So basically, you reduce everything to the problem of three measurements by finding a polynomial time transformation, which gets you back from any higher number of measurements that you might be considering to three. So the main problem is to solve the case of three X-rays. And then you've really got two situations to consider. The directions, if you're talking about the case in n dimensions, which is what we dealt with, two situations. One is where the directions are linearly independent, which is essentially this situation, or the other where they're not, which is the planar situation where you may as well consider those three directions there. Now, it turns out that this is the toughest one to deal with, and to deal with this one here, this is the problem. This answers your question. You map it onto the problem 1 in 3 SAT, which is one of these logic problems. And I can't really go into the details, but of the transformation, which is a little bit complicated. But the general idea is you have to set up some kind of circuit board with an X-ray type problem where you're able to map what happens according to the X-rays in those three directions on that circuit board in the integer lattice onto a situation of trying to decide this decision problem from logic, where you have a finite number of variables, you have a finite number of clauses. Each clause contains 3 literals. That's the variable or its negation. And 1 in 3 SAT is the question, do you have a truth assignment for the variables where you have exactly 1 literal true in each clause? And there's just a little example down here to show you an example of an instance where the answer is yes. If these are the clauses and these are the literals, this is negation here, then this truth assignment, for example, gives you this one is true, right? X2 is true, so the negation is false, and X4 is false, so this is the only true literal in this clause, and so that is consistent with the 1 in 3, a yes answer to the 1 in 3 SAT problem. So that was the general idea. It would be a separate talk to go into any more details than that.
But when you talk about running time for your X-ray problem, you mean
Yes.
polynomial in the number of atoms, or in what? What's your measure?
In the number of atoms, right? Yeah. All right. So it's bad news all around. Non-uniqueness. No matter how many X-rays you take, and unless you just take 2, which doesn't give you enough information, you're not going to have polynomial time algorithms. So let me spend just a few minutes talking about a class of sets where you can get some better results, although this is really, to be fair, I should go over here, shouldn't I? Well, you don't. You don't. I mean, in certain special situations, such as the one I'm going to describe right now, then there are preferred sets of directions. But this is for special classes of finite sets. For the general problem, where you don't have any restriction, there's no particular reason to take any finite set of directions over any other finite set, except you've got the physical restrictions, so you can't take more than 3 or 4. If you're trying to take real-life measurements, you're restricted to few measurements, and you're restricted to directions which have low integer coordinates. But otherwise, there would be no reason to prefer one set of directions over another. Who asked the question? I've lost track of you. Does that answer your question?
I mean, I was thinking about on a situation where maybe a direction seems good to you, but maybe the crystal is arranged so that the physics doesn't have enough energy or whatever from the measurement. So you don't see in this direction anything.
Well, I refer all physics questions to the physicists, but it's my understanding that with a general crystal. So typically, what they're trying to do, one typical situation is they have a silicon chip or something like this, and you're trying to determine the surface structure of that silicon chip. So that would be like a real-life type of crystal that they're taking. And I don't think there's any reason to prefer, say, the direction 3-1 to the direction 2-2.
Right. Well, I don't take so much time.
So anyway, it's you can always ask questions about that. Maybe, there's another way of looking at the whole problem. You could take one measurement, look at that, and then try and use the information to help you decide the direction for the second measurement. And schemes like that have been considered in the whole subject. So there's many possibilities here to try. So let me talk about a special class of sets here, which are close to my heart. And that's the class of convex lattice sets. So what's a convex lattice set? Here's one on the picture. These set of big blue dots here is an example of a convex lattice set. That is, a finite set of points such that the convex hull, just stretch a rubber band around, is equal, when it intersects the integer lattice, gives you no other points than those. Okay, so it's equal to the intersection of its convex hull with the integer lattice. That's a convex lattice set. Now, in the class of convex lattice sets, you can say quite a bit more. Let me show you some, again, though, that you don't get rid of this non-uniqueness phenomenon. In fact, this particular set I can use to show you an example of non-uniqueness. So what you now see up here is the blue set that you saw before, and imposed on top of it here is a set colored red. And those two convex lattice sets have the same X-rays in these 4 directions. For example, let me just make sure everybody's still with this. So if I take a line parallel to this direction, like this line here, I count 2 blues and two reds, so the measurement's the same along that line. Okay? So on all lines parallel to those 4 directions, you get the same measurements. Now, it doesn't take too long when you're working with these convex lattice sets to realize, after you experiment a little bit, that somehow this is a typical counterexample. And you get the feeling that they all come in the following way. If I take the convex hull of the 2 sets which give me this example, I get an octagon, this octagon here. And then I can retrieve this example from the octagon by coloring red and blue alternately around the octagon, around the boundary, and coloring inside both red and blue. Okay, and then I get the example up above. But this octagon now is not just any old octagon. First of all, it has integer lattice points for its vertices, so it's a lattice polygon. And then it has another property with respect to these 4 directions. If I take any, if I look in any of these 4 directions, like this direction here, all the vertices match up in pairs. Okay? And that happens in all of the 4 directions. So if I give a name to the directions, like L, for example, I'll call that a lattice L polygon. If you have a lattice L polygon, then that's bad. The corresponding directions are bad if you want to take X-rays, because you have non-uniqueness. So what you would like to do, if you can, is to find a set of directions that doesn't admit one of these lattice polygons, lattice L polygons. Here's an example, then, to show that there are such things with as many as 4 directions. Well, in other work, which actually predates that other stuff with Peter Gritzman, we prove that this is an if and only if thing, so the whole problem does actually reduce to determining whether these types of polygons exist. So if you can show that a polygon doesn't exist with respect to a certain finite set of directions, then that set of directions will be good for taking X-rays. It will determine not all finite sets of the lattice, but all finite convex sets, called convex lattice sets. Well, it's easy to check that 3 directions is no good. You can always figure out a hexagon which has that property with 3 directions. Let me leave that up there. And what about more than 3 directions? We've seen that not any set of 4 directions is good because of that octagon that you saw just now. But what we finally managed to prove is that there are good sets of 4 directions. So it turns out that if you take a set of 4 directions, and here's an example here, so that when you order the slopes in increasing order, and you plug those slopes into the formula for cross ratio, 4 numbers, take the cross ratio of those 4 numbers, if it's not one of these numbers, then it's a good set of directions. In other words, there will be no polygon of this type, and therefore no examples of that type. And if you work out the cross ratio of these particular 4 directions here, it's 5/4. Of course, there'll be many which just avoid this finite set of numbers here, then that's good. So, if anybody actually is ever interested in determining the position of convex lattice sets, this is great. The trouble is nobody probably ever will be. I mean, from a practical point of view, this is not really very interesting. But mathematically, it was fun. We had to use some algebraic number theory, p-adic valuations to get that result. And then using the same, building on that same idea, you can show that actually if you take any 7 measurements, which again is no good, we can't take 7 in practice. But if you take any 7 or more measurements, that would be enough to determine this special class of convex lattice sets. And why 7? What's the special thing about 7? Well, here's an example to show you that 6 is no good. So this is a lattice L polygon for this set of 6 directions. Right? Look in any one of these 6 directions, and all the vertices match up in pairs. Okay, that's enough about that. Let me, let's see, I've got 15 minutes or so. Let me get back to something a little bit more practical, and therefore probably something that I don't understand so well. But anyway, to talk a little bit about other work that people have tried to do to actually try to help the physicists who really want to solve this problem. So I think we have somebody in the audience here that did quite a lot of work, Jeff Lagarius. So, Jeff, if I get this wrong, you correct me. It was some time ago. I think the first thing was LP relaxation methods. Linear programming was attempted as a way to solve the problem. So it's very easy to set this up as a linear programming problem in the following way. You'll basically know that your crystal is restricted to some region of the integer lattice. So label every point in that region with, give it a label, give it a variable. So x1 up to x16, if you know the solution is here, those are the variables which indicate the positions of possible atoms. Of course, x3 is going to be 1 if there's an atom right here. And x3 will be 0 if there isn't an atom there. And then every time you take a measurement, say in the horizontal direction, now look at just one beam of that X-ray, this one here. If you take the measurement 2, it tells you there are 2 atoms on that line, you get the corresponding equation, x1 plus, and so on up to x4 equals 2. And then you've got a system of linear equations, put it into matrix form, and then you can set that up as an LP feasibility problem just by minimizing 0, subject to that matrix equation holding, and with the restriction of the variables being 0 or 1, which is not very nice. So to make some progress, one can do a relaxation and to rather perhaps try to maximize the number of atoms. So now maximize, this is just the number of atoms in your solution, which are subject to the inequality now, that they're less than or equal to the number of measurements, and then you can even relax the variables to have real values between 0 or 1. And then you can use linear programming. And this is a picture from a paper by Fishburne, Lagarius, Shep and Reeds, or some permutation of those people and perhaps others. Fishburne, anyway. And this had sort of become this was a challenge at one time, you know, to as a test for algorithms, try to determine the position of atoms in this crystal here, where ones indicate that there is an atom and dots indicate that there isn't. And using this method, this shows you what comes out. Ones give you a position of an atom, and dots where there's no atom, and these other symbols indicate you've got some number between 0 or 1, and then you have to decide what to do about that. You can round off in some way and then get a solution. Obviously, there are many variants on this theme. I'm just trying to give an impressionistic idea of this method. So this is what came out. This would be what came out. And I think there were 3 measurements taken in the horizontal, vertical, and main diagonal direction here. So that was quite hopeful, although, of course, again, from a practical point of view, this has far fewer atoms than a real crystal. You'll want to have, at least in the hundreds of thousands, and perhaps 1 million or 2 atoms before you can get to the real life situation. While I'm on this side, let me just leave that one up there for you to look at, because it's a nice picture. That's the only reason I'm putting it up. Well, also perhaps to introduce, once again, get back to Peter Gritzman and his group. He's had a pretty active group on discrete tomography for some years now. And on this side I'll put another picture, but I'm going to come back to this in a second. I think I'm right in saying that right now the most successful practical algorithms that have been produced are the ones that have been produced by Peter Gritzman and his group, and they don't use linear programming, but rather just greedy algorithms of various flavors. So I'll talk about this graph in a minute, and over here just sketch those ideas. So what I'm talking about now are results published in the Siam Journal of Optimization, 2000. Of course, all these papers are recent papers. And as I said, they involve several different flavors of greedy algorithms. So here's just the rough idea. Suppose you take, I don't know, let's say 3 or 4 X-rays of a crystal. And now we're going to talk about something of a more or less what's beginning to be a life size, maybe where you have 250,000 possible positions for your atoms, and maybe you know that you actually have 100,000 atoms or so there. So you want to determine the position from these very few measurements. So what you can do is, first of all, if you look at the X-rays, remember these integer-valued functions, you'll have a lot of zeros. I mean, outside a certain range, you'll just have zeros. So if you just look at the non-zero positions and look at those lines and intersect the lines from your 3 or 4 directions, that'll give you a finite subset where atoms might possibly be. So Gritzman calls that the grid, right? So the solution has to lie in the grid. So the idea is to sort of go from inside. So you don't attempt to get an exact solution, but what you want to do is to throw enough atoms in that grid, which are the only possible positions for the atoms to lie, of maximum cardinality, so as many as possible, so that the X-rays of the corresponding set of points are no bigger than your measurements. Okay, so they don't violate the measurements as an upper bound. So it's a sort of inner, that's why he calls it best inner fit. And it's a standard greedy algorithm. The idea is to put points one at a time in 2 bins. The bin F will be the bin where the solution will eventually be, and the bin E will be just a bin of where you throw points where atoms are not going to be. And you start off with both of those being the empty set, and then you weight the points in a very natural way. So just briefly now, how does that weighting go? Well, you take a possible position. This is a point now in the grid, and in one of the lines parallel to your measurement directions. So this is a possible atom. Now you give it a weighting. All right, so here's the atom right here. So you look on this line, and you know how many atoms there should be from the measurement. You also know, that's this number here. You also know how many atoms you've already assigned to that line in the F bin. That's this number here. So this is the remaining number of possible atoms that you can put on this line in the numerator. And then you just normalize it by dividing by the total number of possibilities. So these are all the ones that you've assigned, and these are then the number that are left on the line as possibilities. And now, so that's on this one line, that gives you a fraction. And now you just multiply all the fractions that you get by, there'll be 2 or 3 of these lines, depending on how many measurements, that contain that particular point. So that gives you a weight, and then basically you just award an atom to the points with the highest weights. That's roughly how it works. Okay, that's enough about that. Well, there's a little bit of nice theory. It's amazing that you can get any theoretical result on this, but one result they got was that if you take, for example, 4, m is the number of X-rays, m is 4. If you take 4 X-rays, then this method will give you a solution, or possible solution, which has at least 1/4 of the number of points in the optimal solution. That's not very good. But what happens in practice, what really makes this nice, is that in practice you actually get much more than that. The figure 0.9 is typical. And that takes me back to this these graphs over here. I'll just focus on one of them. It's actually quite remarkable how good the results are. As I said, they have several flavors. They call greedy A, B, and C. A takes the least time and therefore is the least good. C takes a lot of time. But let's just look at C for a minute here. This is a 250 by... No, this is a grid of 250,000 atoms. And you've got a background solution, which you're trying to find, which has 125,000 of those. So that's kind of maximum uncertainty. And if you run the greedy C algorithm, then you get an absolute error of 15 atoms. So you can determine all the positions of atoms except 15 are wrong. That's really quite remarkable. That takes a lot of time to run, apparently.
So what is this 0.9? This looks better than 0.9.
Yeah, this is better than 0.9. 0.9 is for greedy A, maybe under some typical circumstances. But the greedy A is much worse. You see the errors are much worse. I think this is greedy A here. Anyway, as far as I know, those are the best results that we mathematicians have been able to offer the physicists. But the subject's still alive. Let me just tell you in the last few minutes here some other directions which, if you're interested, if you want to pick this up as a research topic, you can go. There are still conferences being held on this kind of thing, and there'll be a workshop, for example, in the year 2005 in New York, organized by Gabor Herman. Lots of different directions the subject's taken. I'm only touching on I've only touched on the physics and the mathematics. There are other connections with computer science and so on. Here are some classes of special sets. We've seen one already. We've seen convex sets. This is actually a special kind of convex lattice set. It's even a polyomino. What's a polyomino? It's something that's all joined up, taxicab fashion. So you can think of arbitrary sets or polynomials, polyominoes, or you can think of sets which have some convexity problem. For example, they might just be convex in the horizontal direction, or they might just be convex in the vertical direction, or just those two and no other. So these are some natural classes of finite sets. And some enthusiastic people have studied the complexity problems. The details here I can easily provide or give you some access to the literature. By the way, there is a handbook of discrete tomography, which gives you some background reading. So this chart tells you what's known in terms of P and NP for these various classes, and you'll see groups of people in France and Italy and Germany who have contributed to this picture, and you'll also see some open problems. The convex situation stands out. The two charts are for two X-rays, so 2 directions, and this chart for 3 directions. And there's some other results on reconstruction from 4 directions, which are the nice ones in the convex situation. So I don't really have time to discuss that. It's just an indication of some possible research areas. One last problem, and then I'm just going to show you a couple of pictures maybe to finish up on this laptop. People have looked at the polyatomic case. So the polyatomic case is where you have more than one flavor of atom, more than one color, if you like. And so now your X-ray is also more powerful. It can register the numbers of every kind of atom in each of the lines in parallel to your given directions. So you get more information, but you've got more uncertainty because you've got several colors of atoms whose position you want to determine. What happens now? Well, of course, it's a harder problem because you've got more colors to deal with. And everything is sorted out, basically, except for the following case, where you have basically everything is NP complete, unless possibly if you just have 2 kinds of atoms and 2 directions, this is unsolved. And it seems to be quite an interesting problem for those of you who are interested in this sort of thing. Several people have looked at that. The case of 3 or more colors was settled by Krobach and Dürr after some work that I did with Peter Gritzman. So they had the best results, and then just this case of 2 colors is left. Now, to finish, if you don't mind me taking these last 3 minutes, I know everybody's anxious to get away for a coffee, and I promise not to take more than 2 minutes here, but having got this far with the machinery, you sure it was the off button that was temperamental? Oh, here we go. One of the very active contributors to this field was a wonderful guy called Alberto del Lungo. I think it's still coming up here on the screen. And this is the cover slide of a talk that he used to give, and he was kind enough to give me this file last year. And I'd just like to dedicate this talk to him because he tragically died earlier this year at the age of 38 of a heart attack, which was a very sad development for the discrete tomography community. Let me just show you a couple of pictures to end up with, and then I'll be able to also show you a slide which has this reference to the handbook. One thing I wanted to say, just in the last couple of minutes, to the young people here. You all think you're doing discrete work, perhaps. You've already labeled yourself as a discrete mathematician. In my humble opinion, that's a bad mistake. Discrete and continuous are connected, and sooner or later, you're going to want to use continuous methods to solve your discrete problem, or vice versa. So I've been talking about discrete tomography. There's a whole subject called computer tomography, or I also have a book on geometric tomography, which treats the continuous versions of all of these things we've been discussing. And from a physics point of view, it goes back to a machine called the CAT scanner, and these are 2 Nobel Prize winners who developed that machine. This is a machine that takes X-rays of a patient and reconstructs 2-dimensional sections for diagnosis, such as these pictures here, for diagnosis or for to help in surgery and that kind of thing. So there's this whole field which shouldn't, I think, be regarded as separate, but connected with what I've been discussing today. I can just show you 1 or 2 last slides on this from this file here. Just to bring that point home, this little chart in Alberto's talk shows the analogy between the discrete and the continuous. So one can talk about X-rays of convex bodies, and then instead of talking about sums of atoms, sums of numbers of points, you talk about line integrals and so on, and you've got a whole family of problems and results in that direction there. This shows, at least as of a year ago, some indication of the current interest in this subject. And there's a reference to the handbook edited by Gabor Herrmann and Attila Kuba, and just some brief indication of the conferences that have been held on discrete tomography. And then finally, I don't really know why I'm showing you this last one here. I've always felt inadequate in trying to discuss the physics of the situation. There it is. Thanks very much. There are some related results of that kind, but I'm not really prepared to say exactly what. at the moment. But there are.
What is the field called? If you were going to look it up, what do you look it up?
Well, if you type discrete tomography, what I've been talking about here, if you type discrete tomography into your favorite browser, you'll get a lot of web pages back. And that's a very good place to start. You'll get surprisingly many. What you were talking about there, there's also a big area around what's called the Radon transform. And the Radon transform comes in a continuous flavor related to the Fourier transform. And then there's a lot of combinatorial versions of the Radon transform. And exactly this kind of wraparound problem appears in that context. But I would have to dig around to provide you some references.